The binomial theorem. What we're going to be talking about today is something called the binomial theorem. Not theorem. That can be a little, tricky, especially if it's kind of just thrown at you. But I'm going to do my best to try and not throw it at you and ease you into what the binomial theorem is and how you're going to be doing it. Essentially, what the binomial theorem is, the definition that you see in the middle, is it's a way of expanding any binomial raised to a positive power, an integer power. So we can't say raised to 1/2 power or to 2/3 power. It has to be an integer, 1, 2, 3, 4, 5, something like that. And for the purposes of our discussion of binomial, we'll kind of accept as simply a polynomial that has two terms to it. So a plus b is a binomial. 3x squared minus y to the fourth is a binomial. And square root of x plus 4 is a binomial. Okay, so those are what a binomial is, and we've seen a lot of binomials in back when we had to do polynomials and how we graphed them and wanting to make sure that we identified what the individual factors were. Well, those factors essentially were binomials. So again, this is the same just definition of what a binomial theorem is. And the reason why I'm putting it to you this way is just so you can kind of see, well, where are we headed with it? Well, a binomial a plus b raised to the 0 power, anything raised to the 0 power is just 1. Okay, so that is, and I know 0 isn't really an integer, but I'm sorry, actually it is. I'm thinking natural number. So now we move to the next pot. So it's not, 0 isn't positive, but it is an integer, and it's the smallest one that we can start with. So a plus b to the first power, well, anything raised to the first power is itself, so that would just be a plus b. Now when we get to a plus b squared, this is where we start having to get into, being able to do distribution properly. A plus b squared, this is where I and any other math teacher kind of lose a bit of our soul if students start doing something like saying a squared plus b squared. This is absolutely not what you should be doing, okay? When we say a plus b squared, we're saying take the binomial and multiply it to itself. Oh, not, I want to write b first for some reason. So we're going to say a, uh, a plus b squared is the same thing as saying a plus b times a plus b, which your Algebra 1 teachers probably taught you the acronym FOIL, says first, outer, inner, last. But what we've seen in college algebra, we recognize, well, all we're doing is distributing the first binomial into the second binomial. So we are going to say a times a and a times b, which will give me a squared plus ab, and then we're going to distribute the b into this other binomial and say b times a will give me another a times b, and b times b will give me b squared. And when we simplify that, we can say a squared plus 2ab plus b squared. So overall, not too challenging, not too bad. Okay, so moving on to the next one, oh, a plus b squared, or a plus b cubed, that's the same thing as saying a plus b times a plus b squared. So we can say a plus b times a squared plus 2ab plus b squared. And you can see that the complexity of this is starting to go up rather quickly. Distributing the a in, I will get a times a squared, a cubed. A times 2ab will give me 2a squared b, plus a times b squared will give me a b squared. So we're just kind of saying multiplying by a. We can pick another number or another color to show when we multiply with b. So multiplying with b, b times a squared will give me another a squared b. So I can put a squared b here. And b times 2ab will give me a positive 2ab squared. And b times b squared will give me a positive b cubed. And combining all of those, we will wind up getting something like this. Here we would say, combining your like terms top to bottom, we would get a cubed plus 3a squared b plus 3ab squared plus b cubed. And from there, even going up to the fourth power or fifth power, you can see it's going to just become that much more complicated. So if you had to do something, say, up to the 10th power, especially if you had to do it by hand, you'd probably be doing it all day. Now, the binomial theorem is something that is used in a few different mediums. Binomial theorem is used in economics to predict the strength of an economy over a course of time. It's used in architecture, and it's used in weather forecasting. So this is something that, while you and I may not necessarily have to encounter this in our daily lives, it is something that is used, and certainly for IP addresses on computers. It's another big application for where the binomial theorem is used. So knowing how this works is important, at least to some people. And this is what the binomial theorem looks like. Because it is taking things that are being expanded out, and then adding them together, that allows us to say, well, ultimately what we're doing is we're saying it's a summation of something. Now, what we're seeing here, as far as in over the 0 like this, and in over the 1 like this, that we'll get to here very shortly. But I just wanted to show you what the binomial theorem was, and really what we're going to be looking at is that guy right there to see how we're going to expand things and simplify it. And it will take a little bit of work, I'm not going to lie to you, but it's not going to be nearly as time consuming or tedious as it could be if we had to do everything expanded out, distributing it manually by hand. So let's take a look at our next example. What does that that n over something mean without that? It's not a fraction. And it's not a multiplication because it's not like saying something times something inside of the parentheses. Well, what it is, it's a combination. So in our previous lessons with combinations, instead of k, we called it r. But at the time, I also said that the n and the r were rather arbitrary. So seeing it here as nck rather than ncr is no big deal. It's just that, well, we're just looking at those two numbers is the combination of the two values that are inside of that elongated parentheses. And the way that we read it is we say the top number over the over the bottom number is we read it as n choose k, or a choose b, or 3 choose 0, or something like that. Whatever happens to be on top, we say that choose the bottom number. So here we would say 8 choose k for the combination that we're seeing. And this is really just a review of what we did with combinations in the past. So here I would say 8 combination 5, or 8 choose 5. And plugging that into the formula that we see here, we would say 8 factorial over 5 factorial times 8 minus 5 factorial. And we'll probably just start simplifying those as we go. Or at this point, you might want to ask me how to show you to do it on your calculator, or look up how you can do the combinations on your calculator to speed things up a little bit. But doing the math is good review, good practice. So a factorial over simplifying the denominator gives me 5 factorial times 3 factorial, and we'll just kind of bring that up here, continue it to the right. Expanding the factorial of the numerator, 8 times 7 times 6 times 5 factorial is where I can stop because I have a 5 factorial in the denominator. And expand the 3, 3, 2, and 1. So the 5 factorial will simplify. So that gives me 8 times 7 times 6 in the numerator. So I will get 336 over 6, which means that that gives me 56 different combinations. Okay, and that's really, again, just a review of how you do the combinations formula, because we will use it when we're talking about factorials. I'm sorry, not factorials, but the binomial theorem. Now here what you're seeing is just some strategies as far as how you want to lay things out when you work them out. You want to, whenever possible, you want to leave a little bit of blanks here in front of your coefficients. Go ahead and just write this down into your notes if you need to, because I'm going to be explaining how we'll do it a little bit as we go, and I'm not necessarily going to refer to each individual one. But essentially what this is telling you is that as you're going to go, the two terms of your binomial, a, b, x, y, whatever they are, the first number of the binomial starts out with n, and the second number of the binomial starts out with 0. And the sum of the exponents of the two binomials as you go needs to add up to be whatever the total exponent of your binomial is. So if the exponent of your binomial was, say, I don't know, 18, a and b, x and y, whatever they are, those two individual exponents as you go continually need to have a sum of 18. And that's essentially what step 3 is kind of explaining to you. And again, we'll see it a little bit more as we work it out. So here, let's go ahead and just go to the next progression of what we were talking about before, a plus b to the 4th power. And let's see how we're actually going to do this using the binomial theorem. Well, here, looking at it, we would say the summation, we would say k is equal to 0, but I'm going up to the 4th power now. So my combinations here, where it says n choose k, that would be, oops, not n choose k. I don't want to write the n again. I want the 4 choose k. And here we would say a to the 4 minus k power times b to the k power according to the formula. Now, what we're going to do is we start expanding it. The summation says the first index start with 0. So I'm going to begin by writing out the factorials, I'm sorry, not the factorials, the combinations of starting with 0. I'm going to say here 4 choose 0 times a to the 4 minus 0 power, which is just 4, times b to the 0 power, which is really just 1. So if you just want to say 1 there, that's fine. And then we're going to go through all of them. And if you notice, the 4 and the 0, that's what that step 3 was saying. The exponents of whatever your two binomial terms are, in this case, the terms that make up my binomial are a and b. The sum of those exponents must equal whatever the overall binomial is being raised to, in this case 4. So 4 plus 0 does give me a sum of 4. And now we're going to go to the next one. So this is what the summation is telling me to do using my combination. So here I'm going to say 4 choose 1. And each time that k value is going to be increasing, because up until we get to 4, because that's what the sum of the binomials that we're going through is 4. So each time that's going to increase, just like what we did in previous summations exercises. And here I'm going to say a times 4 to, or a to the 4 minus k power. In this case, we're going to say 4 minus 1, which would give me 3, times b to the k power, which would be 1 in this case. And we're going to just keep going through that until we've run up through the totality of our summation here. So the next one will be 4 choose 2 to the, or times a to the second power times b to the second power. And then we'll say plus 4 choose 3 and k minus, I'm sorry, 4 minus k, in this case would be 4 minus 3, which will give me a to the first power times b to the third power. And again, the sum of the exponents is still 4. And we have one more to go through here. So you do need a little bit of space on your paper as you're writing these things out. And the more summations that you have, the larger that overall index number is, or the largest exponent that your binomial is being raised to, the more space you'll need. It's not uncommon for you to have 2 complete rows of your paper filled up as you're working these things out. So just keep that in mind as we go. So the last one here is going to be 4 choose 4 times a to the 0 power, because 4 minus 4 would give me 0, times b to the k power, which in this case would give me b to the 4th power. Now what we need to do here is we need to identify, well, what does each factorial simplify to be? And this is where the calculator can become a very helpful tool if you know how to do the combinations on your calculator. But since I don't have a calculator to necessarily demonstrate it for you, let's just kind of work out the individual ones here and see if we can try not to take up a terrible amount of room as we do it, because we still need to plug some things in. So let's go ahead and do the factorials in a different color. So 4 choose 0 is going to say 4 factorial over 0 factorial times the difference of 4 minus 0 factorial, which is just 4 factorial again. And 0 factorial is the same thing as 1. And 4 factorial over 4 factorial, well, it just simplifies to be 1. So I can replace that with a 1. And I don't know, maybe I should do a different color for each factorial, so that way we can kind of see what's being substituted where. So the next factorial, or the next combination, I should say, that we have is 4 choose 1. Well, here, when I substitute that into the combinations formula, we're going to say 4 factorial over 1 factorial times 3 factorial. Well, expanding that out, that's going to give us 4 times 3 times 2, or 4 times, I don't need to go all the way out, we'll stop at 3 factorial. 4 times 3 factorial over 1 times 3 factorial, because 1 factorial is just 1. And you can see those simplify. So 4 over 1, that is 4. So that combination changes to be a 4. So let's do the next one. And ultimately what you're going to see is another pattern ultimately emerging that we'll be able to use to help simplify this a little bit further. So as you go through these a couple of times, you kind of have no choice but to do all of the associated math, and then you start to see a pattern emerge that will help you work things out a little bit quicker. So the next one is 4 choose 2. So we're going to say 4 factorial over 2 factorial times 2 factorial. Well, we're going to get 4 times 3 times 2 factorial over 2 times 1 times 2 factorial, and the 2 factorial simplify, so I wind up with 12 over 2, which is a 6. And so now we can scratch that out and put a 6 instead. And the halfway point is where we're going to start to see the pattern I was referring to emerge. So the next one that we're going to see is the 4 choose 3 combination. And so that'll give me 4 factorial over 3 factorial times 1 factorial. And if you notice, we already saw that here. So we already know that that should simplify to just be a 4. So here I get a 4. And one more combination to kind of look at here. And let me pick a color that'll show up that I haven't seen yet. Let's try gray. I think gray might work. So here we have 4 choose 4 combination. So that gives me 4 factorial over 4 factorial times 0 factorial, which again, we've seen that one already, so we know that that should equal a 1, and we'll scratch that combination out and put a 1. So the pattern that I'm showing you is that the numbers repeat. At some point, you're going to get to a bigger number, and usually in the middle of whatever your expanded summations give you, and you see 1, 4, 6, 4, 1. Sometimes the numbers in the middle repeat before they start descending again. But long story short, those combinations create a pattern that we can utilize. And I'll show you what that pattern is here very shortly. And we want to go back to the black one for our final answer. So 1 times a to the 4th power and b to the 1st power, that also is basically just 1. So 1 times a to the 4th times 1 is just a to the 4th power. And then we have plus 4a cubed b, because b to the 1st power is just b. And then we say plus 6a squared b squared plus 4ab cubed plus a to the 0 is just 1, so that gives me b to the 4th power, and this is what we would, what we would get if we continued doing manual distribution where we had to expand everything out over and over and over again. Now, the first time you do this, it may not seem like the binomial theorem is really much of a shortcut, but part of the reason why it doesn't seem that way now is because I'm taking the time to be clear as far as how we're simplifying things and what's being canceled, or how the combinations are being utilized as we do it. Again, on our calculators, you don't have to show the expanded combinations each time as you do it, but since again I don't have a calculator display to show you how I'm doing it, I have no choice but to actually do the math. And as you do, a couple of these things start to get a little bit quicker as you go. So now let's take a look at, let's try another one, see how that goes. Not trying to get anything too crazy, but now instead of saying variables each time, a plus b, or x and y, or whatever, we have x plus 2 raised to the 5th power. Okay? So let's go ahead. Ooh, I'm not going to take the time to kind of write the formula down, but let's go ahead and see what we get for our combinations. So n, in this case, is 5, and of course we're going to start at k is equal to 0. So my first combination will be 5 choose 0, and then we're going to say a times, or a, or in this case, whatever my first binomial number is, x to the n minus k power. Well, 5 minus 0 is to the 5th power, times 2 to the k power, which in this case is 0, plus 5 choose 1. The k value is going to start increasing because we're going through the summation process. So the first index number was 0. So let me go ahead and, I guess, go ahead and write this out. Here we would say factorial k equals 0 to 5. and that is going to give me uh, 5, not paying attention, 5k of, in this case, x to the 5 minus k power times 2 to the k power. That's the summation process that we're going through. So here I'm going to get x to the fourth, and this is where, if you refer back to the steps, the first term of the binomial, the exponent decreases by 1 each time, and the exponent of the second term of the binomial increases by 1 each time, but the sum of the exponents of those two binomials has to equal, in this case, 5, whatever n happens to be, whatever you're raising the exponent, or I'm sorry, whatever you're raising the binomial to as a power. So the next thing I'm going to get is times 2 to the first power plus, and we'll say 5 choose 2 times x cubed times 2 squared, so that the exponents still have a sum of 5, plus the next factorial, which would be 5 choose 3 times x squared times 2 cubed, and the next factorial, combination I should say, is 5 choose 4 times x to the first power and 2 to the fourth power, and our last combination will be plus 5 choose 5, which will give me x to the 0 power times 2 to the fifth power. Now, let's go ahead and do our individual factorials here, because again, I don't have a calculator to show you as a display how you type it in. So here, the first factorial, or the first combination that we have is 5 choose 0. Well, that will give me 5 factorial over 0 factorial times 5 factorial, which is the same thing as 1. So I'll put a 1 here. And let's pick a different color just to keep things going. The next combination gives me 5 choose 1, which gives me 5 factorial over 1 factorial times 4 factorial. Well, 5 times 4 factorial over 1 times 4 factorial. That just says that's 5. Next combination gives me 5 choose 2. So I will get 5 factorial over 2 factorial times 3 factorial. And the 3's are going to wind up simplifying out, so I'll have 5 times 4 times 3 factorial over 2 times 1, and 3 factorial, and the 3 factorial simplifies, so that gives me 20 over 2, which is 10. And let me pick another color here to keep things different each time. So the next combination that we have is 5 choose 3. So that'll give me 5 factorial over 3 factorial times 2 factorial. And here, this is where we see our first repeat. That's what we just did right here. So I can say that's 10. So here's another 10. And the next one should be a repeat also, but let me go ahead and write it out so you can see why it's a repeat. So the next combination would be 5 choose 4, which would give me 5 factorial over 4 factorial times 1 factorial, because 5 minus 4 is 1. And we see that that's the one that I did in red already, so that will be a 5, so equals 5. And the last one should be a repeat as well, and if it follows a pattern, the last one should simplify to be 1. So let's go ahead, and I think white will show up okay. So let's do the last one here in white. So 5 choose 5 gives me 5 factorial over 5 factorial times 0 factorial, which is exactly a repeat of the very first one that it was in gray. So that simplifies to just be 1. So that's a 1 there. So simplifying everything out for my final answer, I will get, let's go ahead and put the first part down, what we were saying it's equal to. We're saying x plus 2 to the 5th power using the binomial expansion. And again, if you have a calculator, the combinations are going to be that much quicker rather than having to write them out each time. So either way, even doing the factorials is probably less complicated than trying to keep track of all the distribution and like terms that you'd have to go through. That's just my opinion. So the first one is going to be x to the 5th plus 5 x to the 4th. Oh, I'm sorry, not paying attention. 2 is going to be there also. So we're going to say 2 to the 1st power, which is 2 times 5. So the 2 times 5 gives me 10 x to the 4th. So next we're going to say 10 times 2 squared. Well, 2 squared is 4 times 10 gives me 40x cubed. And then we'll say 10 times 2 to the 3rd power. Well, 2 cubed is 8. 8 times 10 will give me 80x squared. And then 5 times 2 to the 4th power. Well, 2 to the 4th power is going to give you, where are we at? 16 times 5. Well, 16 times 5 is going to give you, what is 16 times 5? That is going to give you 80, another 80, so 80x. And then 2 to the 5th power times 1. Well, 2 to the 5th power is just 32. And x to the 0 power is 1, so the final term that we have is just 32. And that is the entire expanded thing. That would be our solution as an expanded polynomial, or as an expanded binomial. Okay? Now, I was referring to that shortcut that we were seeing. Why were the factorial, or why were the combinations repeating itself after a while? They increased, got to a point, and then they started decreasing at the exact same rate. Well, there's something known as Pascal's triangle that is useful in helping us do our shortcuts, or having to figure out what are the coefficients that the combinations wind up giving us. And what we see in our Pascal's triangle is that the first row, when n is 0, is just a 1. And then when n is 1, what we do is we take 1s, and basically as you go down the triangle, the edges are always going to be 1, and then to find the numbers in between the ones, we wind up adding the numbers next to each other to produce the next row. And that'll make a lot more sense when you see it. So as the first index, when n is 0, for our first combination, well, we just say, well, that's 1. And that in the last two examples that we saw, the first combination that we did always gave us 1. Well, the next one, when n is 1, we're going to say, the 1s are always going to be, whatever the extreme row, or whatever the number on the left or the right of the row is, it's always going to be 1. But how do I get the number in the middle? Well, I say 1 plus 1, and that's where this 2 comes from. And then I'm going to say 1 plus 2, and that's where the 3 here comes from. 2 plus 1, and that's where that 3 comes from. Going down in the rows, I'm going to say 1 plus 3, and that will give me my 4 here. 3 plus 3 gives me the 6 here, and 3 plus 1 gives me that. And if you go back to the first one that we did, is the expansion, where we said a plus b to the 4th power, the factorials, or I'm sorry, the combinations that we did gave us these numbers, 1, 4, 6, 4, and 1. Those are the exact numbers that we got. And if you look at the previous example, if we continue going down, I'm going to have a 1 here, and I'm going to say plus here, the 1 and the 4 gives me a 5, which was what the combinations that we got a second ago was. 4 plus 6 gives me a 10. Another 6 plus a 4 gives me another 10, which are the coefficients that we got from the combinations that we just did. So 4 plus 1 gives me another 5, and then finish it off. Oops. I don't know why I want to put a T. Finish it off with just another 1 at the end of the row. And Pascal's triangle, even if you don't have a calculator to help you with the combinations, is a way of figuring out what those coefficients would be without having to actually do the combination formula. But, well, again, you don't get to the shortcut until you see how the long way is done first, usually in math. So now we kind of see how that's going to help us out. So here's our next example, and this is really going to be the last one that we use the theorem for expansion. And looking at this, as we would say, using our summation, we would say k is equal to 0. In this case, the index number goes up to a 5, so we're saying the sum of the first 5 again. I'm sorry, in this case, let's change it up a little bit. Let's change that from a 5 to a 6, just to make things a little bit different, and use the Pascal's triangle for us. So let's say that's 6. So I would say for my combinations here, I would say 6 choose k. And then I would say the first term is 3x to the, and I'm going to put that in parentheses, to the k minus, I'm sorry, n minus k power. So I'd say 6 minus k power times a negative y. So I'm going to put that in parentheses also to the k power. So that's how we're going to kind of follow it out. So I'm going to go ahead and start by writing out the overall expansion using the combinations where we say, 6 choose something, and see what we get. So I'm going to go ahead and start it out and say we'll have 6 choose 0 for our first combination. And then I'm going to keep the term, the 3x in parentheses, and you'll understand why I do that here as we go. So I'm going to say 3x to the 6 power times negative y to the 0 power. And then the next one gives me a factorial. I'm sorry, I keep wanting to say factorial. Combination of 6 choose 1 times 3x to the 5th power and negative y to the 1st power, plus next combination would be 6 choose 2. And I don't think I'm going to be able to get this all in one row because we're the 5th, going up to the 5th one, stretched me from edge to edge on my board. So I think I'm going to have no choice but to do this in 2 rows. We'll see how it goes. So here I'm going to say 3x to the 4th power times negative y to the 2nd power, plus the next combination would be 6 choose 3 times 3x to the 3rd power times negative y to the 3rd power also. Ooh, that was the worst looking 3 I ever drew in my entire life. Let me fix that 3 here, clean it up a little bit. And yeah, I'm about out of room here, so I'm going to kind of keep going, continue down, so I'm going to indent it a little bit, plus, and the next combination will be, yeah, I just want to keep it the way I am. I think I'll have room to finish everything. So the next combination will be 6 choose 4 times 3x to the 2nd power times negative y to the 4th power, plus 6 choose 5 times 3x to the 1st power times negative y to the 5th power. And the last one will be plus 6 choose 6 times 3x to the 0 power times y, negative y to the 6th power. Now let's use our Pascal's triangle a little bit, and if you have it handy from your notes, you don't necessarily have to write it down again, but since I don't have it handy, I'm going to go ahead and write out my Pascal's triangle kind of real quick. So I'm going to say when n is 0, I get 1, and then I'm going to do 1 and 1, and then I have 1, 2, and a 1, and then a 1, 3, another 3, and a 1, and then I'm going to have a 1, a 4, a 6, a 4, and a 1, a 1, a 5, a 10, a 10, and another 5 and a 1. And those were the coefficients that we got on our last example. So this is when n equals 0. This is when n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. Well, we're going up to the 6th power, so I need one more row in my Pascal's triangle. So I'm going to say a 1 here, and then I'm going to get a 6, a 15, a 20, another 15, another 6, and a final 1. So here's when n is equal to 6. So using the Pascal's triangle, I can say this here is going to be a 1, a 6, a 15, a 20, another 15, another 6, another, and another 1. So those are the coefficients that we're going to have as we work it out. And I'm going to pick a different color so everything doesn't blend together as black or blue. So let's try purple here. All right. So now I want to look at the, let's simplify it out a little bit. So we're going to say 1. Now 3x to the 6th power is the same thing as saying 3 to the 6th power and x to the 6th power. Same thing here. It's like saying 3 to the 5th power, x to the 5th power. That's why I wanted to keep it in parentheses. Okay, so as you can see, that's how we're going to follow through. So the next thing I'm going to get is, so 1 times 3x to the 6th power is the same thing, like I said, is saying 3 to the 6th power times x to the 6th power. So 1 times 3 to the 6th power is going to be 729 x to the 6th power. And anything to the first power is just 1, so negative y to the 0 power is just 1. So that is our first expression. And now we're going to say, okay, well, 6 times 3 to the 5th power. Well, 6 times 3 to the 1st power, or 6 times 3 to the 5th power, I can't speak right now, is going to give me 1,458. So 1,458. Now you notice I didn't put a plus or minus sign here yet because the next thing that we're kind of looking at, well, I have negative y to the 1st power. That's like saying negative 1 to the 1st power and y to the 1st power. So negative 1 to the 1st power, that's going to give me a negative. So I'm going to have x to the 5th power, y to the 1st power, but because y is negative, the overall number becomes negative. Anything raised to an odd power will be negative. So moving on. Now I'm going to say 15 times 3 to the 4th power. 15 times 3 to the 4th power is going to give me 1,215. X to the 4th power, and y squared is a positive number, so I'm going to say y squared, and overall the whole thing will be positive. Moving on, next expression, 20 times 3 cubed is going to give me 540 x cubed, y cubed, and because y cubed raised to an odd number is negative, or negative y raised to an odd number is negative, so the overall number here is negative. And my Pascal's triangle is in the way, so I'm going to keep going down in the second row, and which is okay because this is about where we should be in our second row. 15 times 3 squared is going to give me 135 x squared y to the fourth, and negative y raised to the fourth power is a positive number, so I'm going to say plus 135. And continuing on, 6 times 18, I'm sorry, 6 times 3 is 18 x y to the fifth, and since y to the fifth is a odd number, that will be a negative number overall. And then we finally have anything to the 0 power is 1, so this is really going to just say plus y to the 6th power. So this whole thing is what 3x minus y to the 6th power expanded out would be. Now, like I said, this may seem like it's a lot of work. Just try doing it manually, expanding it out, expanding it out, expanding it out, 3x minus y 6 times, and I guarantee you're going to find this is, as complicated as this might be, doing it by hand, much, much quicker. Now, the last thing we're going to look at for our binomial theorem, no more expanding for the time being. We'll save that, the rest of that for your homework, is how can you use the binomial theorem to determine what is a specific term? Like what is the fifth term of something raised to, I don't know, whatever power. And this is the rule that we see here. So still looking at a combination where we say n choose k minus 1 times n minus, and in parentheses, k minus 1 times b to the k minus 1 power. This is, again, just we're going to utilize the fact that people have already demonstrated this pattern for us. I'm not going to try and demonstrate the pattern for you yourselves. You can easily go back to any of the other, any of the 3 examples that I've given you, as long as you don't try to go, as long as you don't try and pick a number like the 20,000th term, because none of the ones that we have had that many numbers. As long as you pick something that is, within the answers that we picked, is, like if you want to know what is the 3rd term or the 4th term, you can find those out using this example with the 3 expanded binomials that we've already done. So having that down, now we can say, okay, well, what is the 6th term of x plus 3 to the 10th power? Well, here I'm going to write it out like this, is I'm going to say the kth term is equal to, that's how I think of it, is the combination of n choose k minus 1 times a to the n minus parentheses k minus 1 power times b to the k minus 1 power. Well, that says, in this case, here, the way I think of it is n, in this case, is 10. That's the exponent that we're raising the binomial to. K, well, that's the 6th term that we want, so the kth term in this case is the 6th term. And A, in this case, is going to be x, and B, in this case, is going to be a positive 3. So those are the numbers that I'm going to substitute into here. So what we're looking for is the 6th term, and we're going to say a combination of 10, and so k minus 1 would be 6 minus 1. So here we'd say 10 choose 6 minus 1 times x to the 10 minus 6 minus 1 power times, in this case, 3 to the 6 minus 1 power. Substituting those things in is the hardest part, really, of your math. So, maybe the combination that you're going to see here. So we have 10 choose 5 when we simplify the combination inside that elongated parentheses times x to the, 10 minus 5 power to the 5th power. And then we're going to say times 3 to the 5th power. So off to the side here, let me pick a different color. to do my combination with. So I'm going to say 10 choose 5 would be 10 factorial over 5 factorial times 5 factorial again. So I'm going to get 10, 9, 8, 7, 6, 5 factorial, and 5 factorial times 5, 4, 3, 2, 1. So the 5 factorial simplify. 10 times 9 times 8 times 7 times 6 is going to give me 30,240 over 120, which overall is 252 combinations. So I'm going to say, coming back to here in purple, I'm going to get 252 times x to the 5th power. We can put it inside the parentheses if we want to. And 3 to the 5th power is going to be 243. So if I multiply the 243 and the 252, that is going to give me the 6th term to be 61,232 x to the 5th power. So that's the 6th term of the binomial x plus 3 raised to the 10th power. Last example that we're going to look at, and I understand this is running a little long, so thank you for bearing with me, but, it is a slightly complicated topic that needs to have a little bit of context and explanation applied to it. So here, looking at this one, I want to know using the formula, I'm going to say the kth term is equal to here, the combination n choose k minus 1 times a to the n minus in parentheses k minus 1 power times b to the k minus 1 power. You don't have to write that down every time, but it's just a habit. I think it's good math practice. Anytime you use a rule, write it down. So here, looking at the variables that we're going to substitute, n in this case is 12. That's the exponent of the binomial itself. K is the term that we're looking for. That's the 7th one that we want in this case. A, the first term of the binomial, in this case will be 2x, and b, the second term of the binomial, in this case is a negative 1. Substituting those numbers into the problem gives me the 7th term is what we're looking for, and then I'm going to say 12, and I'm going to go ahead and just simplify these straight away rather than trying to write them out again. So k minus 1 will give me 6, so I'm going to say 12 choose 6 for my combination. And simplifying here, I'm going to substitute a 2x, and simplifying everything in that exponent, we're going to say 12 minus 6, essentially. So that'll be 6 power here. And then I'm going to say times negative 1, and 6 minus 1 will give me to the 5th power here. Now, the only real math that we have to do is the combination. And again, if you have your calculator handy or your Pascal's triangle handy, you can write it out. But I don't have either of them available for us to really look at right here. So I'm going to go ahead and do my combination. Math, I'm going to say 12 choose 6 is going to give me 12 factorial over 6 factorial times 6 factorial again. And that will give me essentially 12, 11, 10, 9, 8, 7, and then 6 factorial over 6, 5, 4, 3, 2, 1, 6 factorial, and those simplify. So typing that out, all of it simplifies to simply be 924 combinations. So the 7th term becomes 924 times Well, 2 to the 6th power is 64x to the 6th. And negative 1 raised to the 5th power, a negative number raised to an odd number is still negative. So negative 1 to the 5th power is negative 1. Holy cow. Fire alarm just went off. Scared the heck out of me. I think we can finish real quick. I don't think the building's actually on fire, but this is annoying. So I'm going to go quick. Negative 1. So the 7th term ultimately is going to be 59,136 x to the 6th power. All right. Well, that pretty much wraps up the binomial theorem. Hope the klaxon isn't too irritating, but thanks for watching. Any questions, you know what to do. Write them down, bring them to me in class, and we'll see you soon.